The quest to imbue non-biological creations with intelligence is not a modern invention but a deeply rooted human ambition stretching back to antiquity. Myths and legends, such as the bronze automaton Talos in Greek mythology or the golem of Prague, embody the age-old desire to craft artificial beings capable of thought and action. The formal history of artificial intelligence, however, is a relatively recent, tumultuous journey marked by cycles of intense optimism, subsequent disillusionment, and dramatic, paradigm-shifting breakthroughs. This history is fundamentally the story of how philosophy met mathematics, and how mathematics was ultimately amplified by exponential increases in computing power and data availability. The philosophical and computational foundations, pre-1956. The intellectual groundwork for AI was laid long before the first computer was built. Thinkers like Gottfried Leibniz and Ramon Llull envisioned universal calculating machines or symbolic languages that could resolve disputes through computation, essentially foreshadowing the concept of symbolic AI. The most critical foundation, however, emerged in the mid-20th century. In 1943, Warren McCulloch and Walter Pitts published a logical calculus of the ideas immanent in nervous activity, which proposed that artificial neural networks could be constructed from binary logic gates, directly linking the architecture of the human brain to computational possibility. This work was crucial for demonstrating that cognition could be modeled mathematically. The conceptual breakthrough that defined the field came from the British mathematician Alan Turing. In his seminal 1950 paper, Computing Machinery and Intelligence, Turing posed the question, can machines think, and subsequently proposed the imitation game, now famously known as the Turing test, as an operational definition of machine intelligence. A machine passing the test, convincing a human interrogator that it is human through conversation, would be considered intelligent. This paper shifted the focus from building a physical, thinking machine, to programming one, providing a tangible, if highly debated, goal for the nascent field. The final piece of the foundation was the creation of programmable, electronic computers, such as the Atanasoff-Berry computer, ABC, and the Electronic Numerical Integrator and Computer, ENIAC, in the 1940s. These machines provided the hardware necessary to bring the theoretical concepts of logic and computation to life. By the early 1950s, Arthur Samuel had developed a checkers playing program that could learn from its own mistakes, the first true demonstration of machine learning. The Dartmouth Conference and the Golden Age of AI, 1956 to 1974. The formal birth of the field occurred in the summer of 1956 at the Dartmouth Summer Research Project on Artificial Intelligence. Organized by John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, the two-month workshop brought together the era's leading thinkers. It was McCarthy who coined the term, artificial intelligence, for the first time in the workshop's proposal, deliberately choosing it over alternatives like cybernetics, to establish a distinct academic discipline dedicated to creating machines that mimic human cognition. The atmosphere was one of intense optimism, which subsequently defined the golden age of AI research. The pioneers were convinced that the solution to human-level intelligence was just around the corner. Herbert Simon famously predicted in 1958 that within 10 years, a computer would be the world's chess champion. This optimism fueled early breakthroughs in symbolic reasoning. Logic Theorist, 1956, created by Alan Newell, Herbert Simon, and Cliff Shaw, this program was capable of proving 38 of the first 52 theorems in Alfred North Whitehead and Bertrand Russell's Principia Mathematica. It was considered the first true AI program and relied on heuristic search, a method that would define the era. General Problem Solver, GPS. Also developed by Newell and Simon, GPS was intended to solve any well-defined problem by using means-ends analysis, recursively reducing the difference between the current state and the goal state. ELIZA, 1964 to 1966, created by Joseph Weizenbaum at MIT. ELIZA was an early natural language processing (NLP) program designed to mimic a Rogerian psychotherapist. It worked by simple pattern matching and substitution, often turning the user's statements into questions. While technologically simple, its ability to fool users demonstrated the power of conversational interfaces and the human tendency to project intelligence onto machines. This period was characterized by symbolic AI or good old-fashioned AI, GOF-AI, which aimed to explicitly represent knowledge in terms of symbols, rules, and logical structures. Researchers believed that if the rules of the world could be codified, intelligence would follow. The primary programming language used during this time was Lisp, created by John McCarthy in 1958, which quickly became the standard for AI research due to its powerful list processing capabilities. The first AI winter, 1974 to 1980. The high tide of optimism following the Dartmouth Conference began to recede quickly when ambitious promises met computational and conceptual reality. Many of the systems that worked well on toy problems, small, controlled datasets, collapsed when scaled to real-world complexity. The primary challenge was the combinatorial explosion, where the number of possible states or moves grew exponentially, overwhelming the limited processing power of the era's computers. Two events effectively brought the Golden Age to a close and initiated the first AI winter. The Lighthill Report, 1973, commissioned by the British government, mathematician Sir James Lighthill published a scathing review of AI research, concluding that, in no part of the field have the discoveries made so far enabled the promise of the Dartmouth Conference to be fulfilled. The report specifically criticized the failure of AI to move beyond toy problems. The Mansfield Amendment, 1969, in the United States. This congressional amendment effectively halted funding from the Defense Advanced Research Projects Agency, DARPA, for purely basic research, not clearly targeted at a specific military objective. Since AI was primarily basic research at the time, funding dried up for major labs at MIT, Stanford, and Carnegie Mellon. The withdrawal of funding caused AI projects to be cut, labs to be closed, and public interest to plummet. The term AI itself became stigmatized in many academic and governmental circles. The expert systems boom and the second AI winter, 1980 to 1993. AI was revived in the 1980s by a commercial success story known as expert systems. Moving away from the pursuit of artificial general intelligence, AGI, human-level, all-purpose thinking, researchers focused instead on knowledge-based AI targeted at narrow, specific domains. Expert systems were designed to mimic the decision-making process of a human expert. They consisted of two main components: a knowledge base, which contained domain-specific facts and, if-then, rules gathered from experts, a process called knowledge engineering, and an inference engine, which applied the rules to the data to derive conclusions. Key expert systems included MySyn, 1970s, a medical diagnostic system designed to identify bacteria causing severe infections and recommend antibiotics, achieving performance comparable to expert physicians. XCon, Expert Configure, 1980s, developed for Digital Equipment Corporation, DEC. XCon saved the company millions by correctly configuring complex computer orders, effectively acting as a sales configuration expert. This commercial viability led to the AI boom of the early 1980s, driven also by the Japanese government's ambitious, billion-dollar fifth-generation computer systems project, 1982, which aimed to develop supercomputers with robust AI capabilities by the 1990s. This initiative spurred significant private and public investment in the US and Europe, hoping to keep pace. However, the expert systems boom soon collapsed under the weight of its own limitations, leading to the second AI winter, 1987 to 1993. Expert systems proved incredibly difficult to maintain and scale. The knowledge bases, painstakingly hand-coded by human engineers, were brittle. They could not handle situations outside their narrow domain of expertise and required massive, costly updates whenever the domain rules change. Furthermore, the specialized hardware, Lisp machines, developed to run these systems were quickly rendered obsolete by cheaper, more powerful general-purpose workstations, leading to the collapse of the Lisp machine market. The failure of the fifth-generation project to meet its lofty goals only cemented the industry's disillusionment. The quiet rise of machine learning, 1993 to 2010. Following the second winter, AI research quietly shifted its focus from symbolic logic to statistical and probabilistic methods, which eventually became known as machine learning, ML. Rather than codifying rules, this approach focused on allowing machines to learn rules and patterns directly from raw data. This era was marked by several significant, pragmatic successes. Data and compute. The proliferation of the Internet and personal computers dramatically increased the availability of digital data and affordable processing power, providing the necessary fuel and engine for ML algorithms. Backpropagation. Though invented in the 1970s and 1980s, the backpropagation algorithm, a method for efficiently training neural networks, began to be successfully applied to problems like handwriting recognition. Deep Blue, 1997. IBM's Deep Blue chess computer defeated world champion Garry Kasparov. While it primarily relied on brute force calculation and a massive library of opening moves rather than general human-like intelligence, the victory was a powerful symbolic milestone and demonstrated the effectiveness of powerful, domain-specific search algorithms. Shift to real-world applications. Algorithms like support vector machines, SVMs, and kernel methods became staples for tasks like spam filtering and basic image classification, delivering real commercial value without the hype of AGI. Crucially, researchers started marketing their work using less charged terms like data mining or machine learning to avoid the negative connotations of the I label. The deep learning revolution and the AI spring, 2010-present. The period beginning around 2010 marked a seismic shift, often referred to as the deep learning revolution and the current AI spring. This breakthrough was the result of a convergence of three factors. Massive datasets, big data, projects like ImageNet, a massive visual database with millions of labeled images, provided the scale of data necessary to train truly complex models. Increased computational power, GPUs, the simultaneous rise of powerful, affordable graphics processing units, GPUs, originally designed for video games, provided the parallel processing capabilities essential for training large neural networks quickly. Algorithmic innovation, deep neural networks. Researchers, particularly those led by Geoffrey Hinton, demonstrated that deep neural networks, networks with many hidden layers, could overcome previous training challenges when combined with big data and GPUs. The watershed moment came in 2012 when Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton's AlexNet, a type of convolutional neural network, CNN, won the annual ImageNet Visual Recognition Challenge by a staggering margin, drastically lowering the error rate and showcasing the superiority of deep learning over prior methods. This success initiated an explosive growth across all AI domains. Computer vision. Deep learning made object recognition, facial recognition, and image segmentation highly reliable. Reinforcement learning. Google DeepMind's AlphaGo, 2016, defeated the world champion of Go, Lee Sedol, a feat long thought impossible due to the game's vast complexity. This demonstrated the power of deep neural networks combined with reinforcement learning. The transformer architecture. In 2017, Google researchers introduced the transformer architecture in the paper, Attention is All You Need. This model, which relies on a mechanism called self-attention to weigh the significance of different parts of the input data, eliminated the sequential processing bottleneck of previous models, like RNNs and LSTMs, and became the foundation for virtually all modern breakthroughs in natural language processing. Generative AI. The transformer led directly to the creation of large language models, LLMs, like OpenAI's GPT series, starting with GPT-3 in 2020, and BERT, Google, 2018. These models, trained on trillions of data tokens, exhibited unprecedented capabilities in understanding, summarizing, and generating human-quality text, code, and images. The public release of ChatGPT in late 2022 marked the moment generative AI entered the global mainstream, transforming industries and sparking the most intense period of investment, innovation, and ethical debate in the history of the field. Today, AI is no longer a fringe academic pursuit but a foundational technology integrated into everything from search engines and self-driving cars to medical diagnosis and creative arts. The history of AI is a testament to the fact that progress is rarely linear. It is a cyclical process where theoretical ambition meets practical constraint, followed by a dramatic breakthrough enabled by a perfect storm of data, computation, and innovative algorithms. The current AI spring is perhaps the most transformative period yet, shifting the focus from simply analyzing data to actively generating new, human-like content and redefining the very boundaries between human and artificial creativity. This long and winding path from philosophical automata to sophisticated, generative systems underscores the enduring human fascination with creating intelligence, an endeavor that continues to reshape the future at an ever-accelerating pace.